Thank you very much for coming to the talk. My name is Vladimir Vishnevskii. So just working with C++ since a while. And quite often observing some interesting topics that I would like maybe to share. Today the talk will be about the containers performance why I wanted to make this talk, mostly because I find this topic to be interesting and important. So the containers are used almost in every program. Performance of the containers can really be a crucial part of the performance of the whole application. And also it's an exciting topic. There are several disciplines that converge there, so that overlap, and then they meet the real life. This is interesting to observe and research. And the purpose would be not to go through the reference of the containers of a standard library or third-party libraries. We'll be more focused on the primary factors that are affecting the performance of containers. We'll go through them using examples, and we'll just try to elaborate the recommendations and maybe get some feelings about how the containers can be effectively used. So the performance of containers, so containers are the generic classes. They store some collections of data. We are mostly, so in this talk, we'll be mostly concerned with the timings of standard operations. So we are talking about the timing, execution time. And of course, the individual characteristics of containers, they somehow define how they should be used properly within the program. And the performance of the container itself, it depends, of course, on several factors. And let's go through them. Of course, as the container is some data structure, and data structure, they have some algorithms that build this data structure, maintain it, search for items, delete, or make some operations on it. These algorithms, they normally, so their performance is estimated or evaluated using different approaches, and one of them is just using some complexity measure. Time complexity can be as some form of the metric that is estimated normally as the number of operations that algorithm performs. So this is due to the fact that, of course, we cannot just operate by the absolute timings due to just because different implementations or different platforms will have different results, different execution time. And the big connotation is a mathematical concept that normally used to specify the bound of the growth of the algorithm complexity. So growth of the number of operations as the number of items that algorithm is processing increases. And this big annotation describes this growth in the means of standard of the well-known functions. So we can say we can see some graphs here, and this cyan is some timing that we have. This is algorithm, and we can say that so it has the linear behavior. So we can say that it has the order n, like big O n. Complexity, time complexity. We can also see that it actually doesn't matter if it goes straight up or it goes, or if it can be, if it's growing faster or slower. The only matters is that we use the linear function to somehow bound its growth. That means that two different algorithms having like really completely different behavior, they can belong to the same big O group. That means that we cannot just make any assumptions about and compare algorithms based on the big O class. We cannot make any assumption about we cannot compare them. We cannot compare their real life performance based on this. And it's also true that the faster growing functions, they at some point will overtake the slower growing functions. So they will be less performant. But this can happen actually on a quite big data set. So the N can be very, very big. So this should be considered. So these time complexity analysis and analysis of the number of operations can be useful if we really compare to algorithms that perform exactly the same operations but have maybe slightly different patterns there. So for example, here we have swaps. They are the same for two algorithms, but the first one, it just performs the linear number of swaps because for each item it performs one swap. Here we have a nested loop, and this nested loop makes it that for two items in the container, for example, in the sequence, we already have 4 swaps. Here we have only 2. So we can assume that already starting from the smaller data set, the second algorithm will be slower because it has the quadratic complexity. So there are some typical operations that have or designed to have particular big OR to belong to some particular big OR classes. So if we have the continuous storage, we can access each item there just by offset with the same time. So this is called random access, and it has the constant time. So denote as big OR from 1, so order 1. So the traversal of the linear structures is just we are going through each item. So it's linear time, binary search. It's an algorithm that has logarithmic complexity because we do not need to make the search if the sequence is sorted. We just can just split it in half, and this will produce some form of the will be similar to going through the binary search tree that is also here and also has the logarithmic time for look up for some particular item. So the insertion also is quite interesting to observe because so we have, for example, in the continuous storage, the insertion requires that we shift the items that are located after the insertion point. So this is linear from the number of items that we are supposed to shift. Insertion into linked list, just to plug in the new node, it is constant time. The problem is that if we don't know where to place it, because then we need to skip and find the proper position. So this should not be neglected. And also here just some abstract. So we have binary search tree. Normally they are built on the tree structures that are designed to have logarithmic time for insertion. So if we have some disbalance, so we add some item, the tree can become disbalanced, then there will be some rotations that will balance it again. So something just like this. And this is the logarithmic time complexity. But how is it reflected in the real life performance? So let's just try to make some experiments and see. So just some experiments, some basic setup. I was just performing this benchmarking on the Ubuntu, compiler GCC 10. The standard implementations are just from the libstd.c++, so GCC standard library. We have, so on my machine there are 8 cores, it's x86-64 machine, and Google benchmark is used to make the benchmarking. So optimization is on the maximum level. And just as usual, kind of disclaimer, yeah? So we are looking at some relative performance trends, the changes, what is happening there. The exact measurements, they can differ, of course, they will differ on different platforms, different machines, some different settings. So just to be aware of this. So just for our iteration to produce some value, let's just do the accumulate, accumulate. For the on some std vector or std list, standard vector, standard list. So they will we take just the vectors or list. They will be containing int32, and we are just using this algorithm and measure time on the varying n. So what will we see here? Yeah, so we see that, of course, the vector outperforms. So the lower is, the better timing is. So they're just here on the graph, we see that the blue one is vector, and vector is much lower. So, but we see that our expectation that the linear time is substantiated, of course, by these graphs. So they're really growing linear. So there are some outliers, but it's linear growth. And already starting, so here on the graph is the just to fit all, just to fit the whole data set. And here it's a bit zoomed in version on the right. So just to see how, what is the difference for the smaller data set, because sometimes it's important. So why such a difference? let's get into the organization of std_list and std_vector and just analyze it. So here is the code from libstd C++, so standard implementation. So how does the list look like? So we see here, so there is this list node base. So this, it contains the pointers to the next and to the previous item. So it's a doubly linked list. And this list node base is inherited by the list node. This is the main structure that stores the item. And this item is stored in this M storage, just some aligned storage that is there. So the items are linked with each other using this pointer to previous and next, but they, of course, can be located in very different locations within the memory, so arbitrary locations on just as a base case. And the vector is a bit simpler. Yeah, so we have just continuous storage. We have pointer to the start. This is vector impl data that just describes the memory and the items that are stored. So just the storage, so some form of the storage descriptor. And we have m start. So this is the beginning of the items of the storage. Then m finishes is something that the end function returns. So the item after the last one. Yeah. So this is where the last one would be. So the storage is continuous. Why is it important? Yeah. So here we're coming to the caches, yeah, so this is already a bit from the hardware organization. So this is relevant for the platforms that have caches. Not every platform has actually cache, but x86, 64, yeah, so they have, yeah, some multi-level caches. Here is the information about the caches on my machine on which the benchmarking was done. Here, they're just on the bottom right corner. And what is cache? Yeah, so it's a smaller memory that is supposed to compensate the expensive accesses to the main memory, and it is particularly beneficial for the programs that have the temporal or spatial locality of the memory accesses. So that means that if the program, so the spatial memory and temporal locality is that if the item or if the item was recently accessed, then this item or the items kind of nearby will be accessed again soon. So this is, if this is happening, then the cache brings benefits. So in case of the miss, if data is not in the cache, so the penalty for this is quite expensive. So each layer, access to each layer becomes more and more expensive in terms of the cycles that are used by CPU to get this. Here is the what happens with our storage. Yeah, so the continuous storage, it's actually really a good case for cache, because as soon as one item is accessed, the items that are following it are likely to get into the cache. Apart from this, the items with the contrary to this, so the list items, they are not anyhow linked from the cache perspective, so they're just only pointers, so that each item each item from the list to be transferred into the cache should be accessed. So here is this cache grind, cache grind measurement. This is the program part of the Valgrind that emulates the cache and allows to estimate or just somehow get a feeling about the cache performance. So here, to accumulate executions, the number of cache misses are specified. So here they are. That's in bold, and this the first one is for list, and we can see that for the we can see that and for this benchmark 100,000 items were added into the container. So here we see that almost like every second access is a cache miss here. So the performance from the cache point of view would not be really good here. So, but this is important for the systems that have caches. Not every system has cache, as I already mentioned, but anyway, so the accesses to the memory, they still define the performance to a very large extent, because because the memory accesses, they are in general considered to be, and they are in general are, more expensive operations from the CPU point of view. And if we look at the very nice concept that's called iron law of performance that can be used to estimate the time that CPU needs to perform to execute some program, we will see that the CPU time, it is dependent on the cycles per instruction. So this is how many cycles are needed to execute the instruction. And as the memory is more expensive than the more memory accesses we perform, the more time CPU needs to execute the program. And if we look at the disassembly of our accumulate, we will see another interesting thing, that we have more memory accesses in case of the list. So if we compare here, there are, it's actually quite nice, I think, piece of assembly that really shows the loop that accumulate is doing. So here we have the loop, yeah, and R12D is a general purpose register that is used as accumulator. And we add here the item that is pointed by the value that is stored in array X. So we dereference array X here, and this is our iterator. So it is similar in both disassemblies. Here then we increment our iterator by 4 because we have UN32, so we need to go to the next item. And then we compare with the end and we loop back if it is not ended. On the list it's slightly different. So we have our pointer points to the node. Node has these 2 pointers, to the next and to the previous in front. So we need to get the value that we add. So our value is, so we need to add offset of this storage that we saw in the source code. And then to get to the next item, we need to dereference our iterator again, because this is where our pointer to the next is located. So we have one more memory. It will be in the cache already for the systems where there are caches, but anyway, so this is a memory access.
Pessimism there, because it's seeking ahead and then go backwards.
Going.
So you're doing RAX plus 16 first and then RAX afterwards.
So it's not, it just, here is just immediate value. So it's just the address that is taken from the register. It just added, so the RAX value is not modified.
No. What I'm saying is it's accessing 2 locations in the structure, the value and the next pointer, and it's going further into the structure first. So if you swapped around the add R12D and move RAX, would that potentially be a little bit more efficient, because you're then only traversing forwards in memory?
But you need RAX, so the RAX is used in the previous one. So if you modify the RAX, so you dereference RAX and you modify the RAX. So you either need, let's discuss it later. Yeah. I'm sorry for this, just let's keep the questions to the end. Yeah, so, so here the add is, we add the immediate value. The immediate value is, so this is more performant than the memory access here. So I think on the modern x86, so we should expect that this arithmetical is 1 cycle. Here has 1 cycle latency, and here is, I think, 3. Let's go further. So we saw read-only access, so we were traversing the containers. What if we will be actually modifying the containers? And let's do very bad thing here, just do some kind of the inversion, and we take vector and list and we insert it into front. So so we know where to insert into the list, so this is the constant time operation. We just plug in the item in front of everything else. For the insertion of the vector, we always need to shift all the items that are already there. So this is a really bad case for the vector. It's not, so it's something that should not be probably done. But we will just see what is happening if we measure this. And what we see here that, yeah, vector skyrockets here on the large scale. on the smaller scale, we see that up to some point, it's like around 800, so the vector still outperforms. So that means that, so why? Because each item is supposed to be allocated, so there are, depending on how it is organized, but it's heap request to the heap, and up to some number of elements, vector is still capable of effectively shifting the items. So just should be considered, yeah, so that on some different numbers, the performance can be a bit different from what we would expect. How can we improve? What will be the proper reverse? How to do that? Let's do some post-processing. So we can populate the vector in an effective way. Then we can use the external algorithm reverse, and this would produce much better results. So here, the yellow line is our post-processing. So why? Of course, because reverse, it just performs for n items, half of the swaps, half of n swaps, and pushback in general, so it does not shift if there are no reallocation. So in reference, it's specified as having amortized constant timing. So this is something like this here. And yeah, much faster, but if it is possible from the use case, yeah, so if we can split this data preparation with the data access. So let's go further. In C++17, we now have this parallel execution strategies. Let's try to apply parallel version of the algorithm to our problem. For this, we just, so there are some steps required to enable actually compiler to use this parallel algorithm, but generally after everything is prepared, so in our code, we just need to specify here the execution strategy here because the overload accepts this execution strategy. What will we see? The green one is actually worse. Especially at the beginning, it goes up quickly, then on every scale, it's on every size of the data set, it remains, it's underperforms. So why it is so? Basically, the implementation details of these parallel algorithms, they are really implementation details of the standard library compilers backends that I used. But in general, we should be aware that not all that all operations can be actually effectively parallelized. There are also different criteria that need to be met to have effective parallel execution. So the operations should be mostly CPU intensive. Also, it might happen that the overhead of that is associated with this organization of parallelism can just exceed the benefits of parallel execution. So memory access can become the issue as well, and this is the case here. Yeah, sorry. We should consider that it's not always, we should consider that just dropping in the parallel algorithm might not have the results that we are expecting. So what will happen if instead of uint32 we'll be inserting the large objects? Here our vector doesn't have any chance just because we are increasing the footprint of the object, and these shifts, they from the beginning are already not efficient enough to actually overtake the, to be more performant than the allocation. So the increase of the footprint just also affects the performance. So as a small intermediate summary after we researched this particular part, so we should consider that that algorithms that have higher algorithmic time complexity, they can outperform, so they can be better than those that have lower complexity on some particular data set size. Normally at the smaller data set size. Yeah, as they are growing, then at some point this will not be the case anymore. If we can split the preparation of the data, as we did it with the standalone reverse and pushing back the items in some position using just the best pattern for populating the vector, we can get some speed up as well. And parallel algorithms, yeah, so just wanted to emphasize here again that they should be applied with caution. So their application should be evaluated just to make sure that actually they bring performance improvement, and they just cannot be considered as a simple drop-in replacement that we just, okay, so it was a reverse or sort, let's just put in this execution strategy because we know that now it's parallel, it will be executed better. No, not the case. So should be checked. And now, so after we went through all of this, so let's just get some summary of the factors that we probably collected. So first of all, yes, so we have time complexity of the algorithms that are used within the containers. We also have, of course, memory data access patterns. How cache-friendly are they? What generated code we have for particular algorithms plays important role. Also, memory allocation patterns for particular modification of the containers. Also, we should definitely consider what is the nature of the stored elements. So if we can simply shift them, move them, or we need to copy them if they are not movable, for example. And of course, potential for parallelization. So this is something that is also important just to maybe get maximum if it is possible to apply the parallel algorithm. And we are working with platforms where they are implemented. And effective design, yes, should consider this individual characteristics to proper use the containers. Yeah. Okay. So this was the first part. Now let's get to the next one. So we have quite a nice concept that is called sorted sequence. So if we have some sorted sequence, it is this structure in general can be used for various optimizations. So some different queries to the intervals can be effectively done using the sorted sequence. And in the standard library, we have the function standard algorithms, lower bound, upper bound, that using binary search allow us to find the bounds of the interval on the sorted sequence, and we can just then get access to each item within the sequence, within the interval. So we have we have some containers that maintain this sorted sequence internally. For example, set or map. They have these built-in functions. So we have member functions, lower bound and upper bound. And normally, just to access some interval, we have logarithmic time to find the bounds. Twice we need to find the lower bound and upper bound. And then we need to have. And then we just access every item. And we do not need to access the whole set to find some items belonging to some interval. So let's see how we can build and modify and access the sorted sequence. So we will be benchmarking first insertion. So we will be working with the sequences that are holding uint 32. And so we will first compare set and vector. For set, we have member function insert. It already maintains the order. For the vector, we need to use lower bound to find the proper position where we insert the where we insert the new item. So we just check if it's not there because we want to maintain behavior similar to set. So it's not multi-set set, so a collection of unique items. So, and for the insertion, probably we can already expect this, yeah? So that we have quite a bad performance for the insertion for the vector. We are not putting in front every time, but we are generally still shifting because we are just placing it in some arbitrary positions. For the set, we just have logarithmic complexity, and we need to create the item and plug it in and rebalance. So this is designed to have logarithmic time. So, but again, similar thing. Up to some number of elements, actually, std vector outperforms. In my measurements, by the way. So what improvements we can do? Just already having experience from our insertion into front experiment. So first of all, yeah, one important thing, yeah, we can improve allocation for the vector. Just pre-allocate everything using reserve. That is recommended to do if we know the number of elements that we will store. This is one improvement. The second improvement, let's do this post-processing thing. So just push back items, then sort it. And then also try to apply the parallel algorithm again. Maybe this time it will work for us. So, and what we will see here, yeah, so here on the right, it's a bit, the vertical axis is shortened a bit just to have these well-performing algorithms, well-performing options visible. So for us, what we see here is that of course, so this post-processing are working very well. And here, by the way, our parallel gives us a performance boost. Because parallel so the parallel algorithm seems to be working well on this sequence. And we also see that, of course, other versions that we have, they are, so the versions where we just inserting into correct position, they are poorly performing. But reserve provides some improvement. So this was improvement for the vector. Let's think about the set. We have set as well, so let's try maybe to improve it. So the issue is the allocation of each item. So some problems from this can be solved using the allocator. Allocator out of the scope of this presentation. Just let's there are a lot of information about this, but it will be really we need much more time for this. But what we can do, so we have some alternative implementations. For example, there are implementation of that are compatible with std set that actually are using different allocation models. There is a framework that is designed for game development, Electronic Arts STL, that has these so-called fixed capacity containers that are using the storage where the items are allocated in continuous storage. It's still set, it's still null, it's still tree, but the items are just taken from the continuous pool. They are linked together, but the allocation doesn't require to request heap all the time. And so the fixed set here can be specified. It can be completely static, so the node count can be specified as a maximum node count, so the static storage will be used. Or there can be overflow allowed, then the allocation would be happening from the heap, but still the storage will be continuous. So our fixed set actually, so this is the cyan here, so the fixed set here, it's here, yeah, but it is better than just a normal set, but our post-processing versions, they are better. So we saw that to have the vector, to keep it sorted, we always need to find we always need to use the external lower bound method. We need to check if the item already there. So it's actually still vector with some external algorithms. It doesn't have semantics of set. So there is an alternative. just in the boost container library, there is a so-called flat set that actually does exactly this. So it uses this binary search to get the positions, and then similar, so providing the APIs compatible with set, but having all the items just in form of the sorted continuous storage. It's an adapter, so some random access container can be specified to store the items. And I will be using this one further, so it has the same timings, because this is something that we will do manually if we will need to maintain the same sequence. So just, and yeah. And so this flat set, it has also an interesting feature. So we can extract the sequence from this, so the underlying container, we can process it again, and we can return it back. So that means that for some operations, we can use external algorithms as well, and we can also prepare it so we can use the vector, fill in it, sort it separately, and then just put it in, and we will not need to pay this overhead for inserting in some position. So we can also do this post-processing for this particular data structure as well. So this adopt sequence just consumes the sequence that we can provide, and extract sequence just gives us sequence. So that's what we can do. So this is the underlying container that is used to store the items of this flat vector. Okay, so now about the search. So search in the sequence. So we have here, so we see here that we have quite a good performance for the flat containers. So this is due to the fact that we have the random access, and we have good locality. So especially as the intervals where we search by the binary search become smaller. So this is for search. Yeah, so we see that, yeah, so here we can see that's the red one here. Boost flat set has a good performance. Just one remark, I put the star there on the previous slide. So the correct name of the fully qualified name is Boost Container Flat Set. I'm using here Boost Set. This is not correct. It's not in the Boost namespace and Boost Container, just to make it shorter. Just, yeah, so. Here, the small type. Here it's. Yeah, that's what we saw. Yeah, so we will come back to this a bit later. Yeah, so but thanks, this is true. The bigger items are the less cache friendly. The less cache friendly the program will be. Yes. And for the deletion, we have a similar issue that with the insertion, because we need to shift items just to every item that is located behind the item that we need to remove. So every item we need to shift. And here it's a similar issue. And if but it can also, there are some ways how we can theoretically, if it is possible, we can mitigate this. So the best case would be just not to delete. So if it's possible, not always possible, but if it's possible, so we can just discard items. As a simple structure to have it, we can have a map where the key will be our value that we store, and then we can have the some flag if the item is still valid or not. Can be, I mean, if it's some object, it can store some. There can be some property for this, but the idea is that we can just have. We can just mark the object as discarded, and then at some point, if we need, have several objects deleted as well using erase remove idiom. This is the one that is quite important, because this makes one single pass, just moves every discarded item to the end, and then just removes them all the time. So there's no shift for each single item. This is one of the very old suggestions to use erase remove, still of course valid and should be used. So something like this. But this will, yeah, so if we just remove every 100th item, so on every 100th item we perform this, we will of course have a significant drop here in the timing. So this is the green one, so it's much better than this red one. Yeah, so this will be better. But it has the trade-off. So the insertion will become a bit more expensive if we are doing it just as a straightforward insertion, because now the footprint increased, and so we need to shift more. And then also but we can, with the flat map, we can use the same trick, so we can extract, so we can just prepare the sequence and just give it to the container. So this post-processing thing helps us as well here. And we also will have the trade-off. So if we do the accumulate, for example, if we do the traversal, because we need to check if the item is discarded or not. So we have some more code to process. Yeah, so this, because this is in the container. Now, like if we don't need the sorted sequence, we can use unordered containers. Yeah, so this is something that is specifically designed to have a good performance on insertion, deletion, and search, first of all. So we can have different types. So there is it's based on the idea that we have some function that from some key produces the key hash value. Then this hash defines where the item is located. Several keys that will have the same hash, so that will collide. They will be located in some either bucket or in some continuous storage, depending on the model that is used. And then as soon as the correct location will be found where the item should be, then every item there will be compared to have exactly the same key. Yeah. So regardless of this, yeah. So we have. Yeah, so we have unordered set and unordered map. These are the parts of STL that we can use. We also have AppZell. So this is the framework that's quite well known. So that is maintained mostly by Google. So it has the flat implementations. So where the storage is flat. And for the standard one, this model is used. Yeah, so with the buckets where the collided items are located. So the insertion here, it's like the best performing versions here. So unordered set is signed this orange one, or actually even brown here on this coloring. So this like really low here, there can be seen. On the smaller, by the way, we see that actually the unordered, we see that the unordered set is slightly less performant at the beginning if we compare it to our kind of post-processing. But this is slightly different, different data structures, and they has different purpose, but I just put it here for the comparison, as we have this insertion operation also measured for another containers. So for the search, yeah, they are also best performing. So we have here green, and also it was orange originally, looks more like brown here, there's two. Those are so we perform search of some random values that are inserted in the container. And even for traversal, just going through, it actually also has quite a good performance. Surprisingly for me, unordered set actually outperforms this flat hash set. It's a consistent result. I remeasured it several times, but I have some assumptions why this is happening. But generally speaking, yes. So on the larger scale, so we see that they are performing as the items, they are not completely disconnected for an unordered set and for the flat hash set. So the performance is actually quite good. For its, I would say that these data structures are probably not designed for this kind of use case. So and for the deletion, similar. So they are designed to have high performance of the deletion, so also kind of best performing containers here. And yeah, this is about the containers, about the sorted sequence, and about the unordered containers. Now, as we saw that there are some characteristics of these sequences and containers, let's just have a look at some case and just go through some optimization steps where we will be just combining some individual strengths of the containers just to get some, just to improve performance of some particular logic. So we have we are given n records. These records, they have strings as labels, and we need to be able to query this set of records to get the labels, to get the items that have labels in the interval according to their lexicographic order. So we need to compare strings. So the trivial solution would be just to use, so we need to count the items that are within the range. So we have the count if algorithm that we can just apply. Compare the strings. So every time here we will have the strings comparison. This will be our best case. Will be our base case for our improvements. So we check every string. Of course, we have the linear complexity here. It grows linearly, so this is kind of expected. And so first thing, let's reduce the indirection. Let's store the string in line. This is another thing from this ESTL framework. We have there similar to set, we also have the fixed string there, so where the storage can be pre-allocated and actually static. We need to know the maximum size. Let's assume that we know it. In some cases we know it, in some cases not, and then it's not applicable. It also increases the footprint of the object as well, so it also can be not applicable, but in some cases this can be a solution. So let's just see how this would affect the performance. So now it's actually better for this count if linear approach. So the comparison, and so we do not do the indirection. We do not so the string is stored in line, so we do not have extra memory accesses to some independent locations. Yeah, so we just going through our continuous storage where the string is located. Okay. The next approach that we can use. What if we just collect all the labels, do some pre-computation? So we just collect all the labels, we sort them, their position will define some ID. And we assign this ID instead of labels instead. So that we just mapping the string to some ID that corresponds to its position into the sorted order. So for this, we can use an ordered map of or a flat hash map to map this, and then we prepare this mapping. From this mapping, we can get the values, and we use again this linear traversal in count if just to check if it's there or not. So we just reduce comparison of strings, and yeah, this gives us the better performance. Why? Because now we do not compare the strings at all. So I mean, it's quite logical, yes. So would expect this, yes, something like this. And we have two implementation measures. This yellow is with unordered map, another with the flat hash map. And at the beginning, so the unordered map is slightly less performant because when the contribution of this timing, so it's less performant according to our measurements for search. So when this contribution is more significant on the smaller data set, then it's just completely, it's just already not visible then when it goes to the, so they are basically, so the measurements are equal for both of them almost, yeah, so up to some error. So, but yeah, so in these two approaches, they're working well. So another approach, yeah, we can use the sorted sequence because if we so far we were just scanning the whole data set, picking up the correct items. Now, if we store them in the sorted sequence, we can just find the range there. And we use for this flat multi-map because we can have the labels are not unique. And we can also use one where the key is just a standard string, another one is our flat string. And here we just use lower bound, upper bound to find where. And here, what is also interesting, so also worth of consideration. So we do not need to traverse them. Now we just, in the continuous storage, we can use std distance just to get the number. So what is interesting here, so now we actually, so if this is our task, if we don't need to scan them, so here we reduce the complexity of this algorithm because it's already not linear, it's actually logarithmical because we just need to find the ranges. But this will require more of a pre-computation, so we need to build it. But we have a feeling already what we will face if we will need to do this. Yeah, so because we saw how expensive how this can be arranged or optimized. So this would give us, now I need to rescale all the time because otherwise they are not visible, they merge all. So just by the vertical axis, I just reduce the scale here. So here are these flat multi-map and flat multi-map with the string. This is orange, and cyan here is this with the fixed string. So the fixed string is better because we saw that because it is again, so it is stored inline, less allocations. So we have the better performance. We can improve also the key comparison and also the access to the key. So, and the last. Let's use, instead of string, let's use our actually IDs. Yeah, so because what we did before, so we have these IDs that correspond to the position in the sorted order. Again, requires pre-computation, but we just removed, instead of string, we just use the ID as the key of our multi-map. And here it's like the best performance, the blue one here. So because here we have, like the structure is completely flattened, what is stored in the map. We do not have expensive string comparison. We have smaller object size, the smaller footprint, and for that we just need to have one. We need to have two map lookups to get the IDs by the to get the IDs by the string, by the label. Okay. So. Just a summary for this particular case. So we see that, of course, if we minimize the memory indirection, we already get some improvement in performance. If we reduce the complex types using mapping, for example, into simpler types and perform operations on the simpler types, this also gives us benefits. So it also gives us speed up. So, of course, pre-computation can be really like a base of the performance improvement. So we tailor the data structure for particular use cases. And yeah, we saw that. So we have the sorted sequence. It works very well for the queries to the intervals. At the same time, if we just need to insert, check that something is in the collection and find this in this collection, then and then probably remove without the queries to the intervals and where the order does not matter, then the unordered hash-based containers, they can perform better. Okay, so I think almost last remark. Actually, we're coming to the conclusion. So in general, so we saw that indirection brings overhead. So if we just need to access some memory addresses, then we can have cache misses. We have more complex generated code. So if we, for example, here we have two containers. They are actually owning some records. They use the pointers. So they own them indirectly. They have the pointers to them. So this is something that we will probably have with the objects that have a large footprint. We will, and we need to perform some accumulate on them, so just to get some value out of it, if the key is odd. Yeah. So just a simple example. So in this case, and we can store and approach it differently. So we can have vector, or we can extract the key as some key to the flat map. So here it's just simple. So I do not use lookup by this key. It's just something that is stored inline. The interesting thing here is that in case of the flat map, we access the record only if the condition is met. So even if these if the key that we extracted here is odd, yeah. So we are checking and in case of the vector, we always need to access by the pointer our object, and in some case once, in some case twice. So what would be the difference? Yeah, so the difference is quite visible. Yeah, so for this accumulate, so the flat map performs better. Less indirection, less accesses. So this is just to describe that if there is some essential data that is frequently accessed, so might be it's worth of extracting it and storing it separately and having reference to the whole object. This can bring some improvement. Also, of course, increasing the size of the data as we are copying some of it, or maybe we don't need to copy, maybe we don't need to store that in the object as well then afterwards. So, but these patterns are important. Okay, actually, this was now it's almost the last slide. So, just a general conclusion, what I just wanted to in general to say. So, we can reason about some performance. We got probably some feeling about what we can face, what we can get out of some containers. At the same time, we need to evaluate, we need to measure to make sure that actually our design decisions work for particular sizes, for particular use cases. So this is important. So this is a fundamental thing. We also have third-party containers that solve a lot of problems for us. Should not be neglected. Most of them are just open source, well maintained, well used, so nothing the one should be probably afraid of. So we can combine containers just to form a better application patterns. If we can use container in a read-only mode, just prepare data and then accessing it, this gives benefits, but not always the case. But yes, if it is possible, just to design it in a way that if it can be done, then it can improve. And yes, parallel algorithms, just one more time, they can bring performance benefits like we saw with the sort, but at the same time, it can also reduce the efficiency of the program like we saw it with the reverse. So just should be used carefully. So, yeah, questions. Thank you very much.